Have you ever felt that weird feeling or sensation when you're in an elevator and it accelerates really rapidly? You feel yourself being pulled down to the ground, or when it slows and you feel yourself being a little bit lighter? That's due to G-force, the apparent feeling in your change in weight. And of course, if you've ever been on those rides at amusement parks, you get it even worse than that, especially those ones that just do a drop. So G-force is something that astronauts experience when they want to be launched into orbit with the rest of their payload. So let's look at some examples to see what's going on here. Now, I've got some equipment here, and we're going to do a comparison of the forces here. I'm going to do a spring balance. Now, the spring balance I've got here is a demonstration spring balance. Okay, it's not quite zeroed, which I'm not very happy with, haven't bought it, but anyway, it's a little bit off, probably about, just a little bit less than 1 Newton. So as I pull this, it moves around and shows you the change in newtons, right? So we'll use that, and let's just draw that up here. So if I put a 1 kilogram mass on the end, let's see what it reads. Okay, it should read roughly about 9.8 or 10 newtons. As you can see, it's a little bit off that because I said to you before that it is not quite zeroed. So let's just pretend that it's 9.8, or let's make the maths easy, 10 newtons, right? So at the moment, if I hold it very steadily, this whole system is not going up, it's not going down. We've got gravity pulling down on the mass, and that pulling down of gravity is giving us a deflection of the needle and showing us the weight. Remember, weight is a measure of the pull of gravity on an object, right? Which is different to mass, which is actually the amount of stuff that's in this mass here. So the mass is measured in kilograms for weight, and for mass, and weight is measured in newtons, right? So let me just put that down for a second, and let's draw some bits and pieces on our diagram here. So we've got the little needle there at about 10. We've got a force acting upwards and a force acting downwards. We already said that the force acting downwards is the force of gravity, Fg, got an arrow at the top to represent the vector, and that's equal to mg. Okay. Now we've got a force acting upwards, because if we didn't have a force acting upwards, then the whole thing would be moving in a downward direction. Since I was holding it up and it was stationary, we can say that the forces are in equilibrium. The downward force is equal to the upward force. So there has to be an upward force. And for our instance here, the upward force is the force of tension. Okay? And we can draw what's called a free body diagram for that. So then we have the force going down, Fg, and the force going up, and it should be the same size, opposite direction, T, right? So that's what's going on in that instance there. Now we're talking about forces in one direction here, in one dimension, the y direction. We're not talking about anything in the x direction, only in the y direction. So if we think about the sum of the forces here, right? So the sum of the forces, which we can call F net, and it's in the y direction, so we can put a little y there. So the sum of the forces is the forces going up and down. Now whenever we do this, we need to make sure that we designate which way is positive and which way is negative. And normally acceleration is the direction in which is positive. So for this instance, I'm just going to call up as positive and down being negative. Okay, so the force going up is the force of tension, T, plus the force of the gravity going down, and we said that was minus, so we have to go minus mg. And because the whole system was not moving, it was stationary, we say that the sum of the forces is 0. I was holding it steadily and it wasn't moving up and it wasn't going down. So F net is 0. And so therefore we could say that the force of tension is equal to mg. Now we know mg is the term for weight, right? Your weight is mass times the acceleration due to gravity. So we could go weight is equal to mg. So what are we saying there? Well, we're saying that what you feel at a what this feels is that this scale is measuring the weight, the apparent weight of the object, right? Now, if I was to talk about that in terms of G, well, how can I write this over? I'll probably put it here. G is equal to the apparent weight of an object divided by its true weight. And so here we can see here that it's actually measuring the apparent weight. In this instance here is mg. The true weight is mg. So therefore 1. So the G force of that system is 1. Let's look at it in terms of a rocket. Okay. Looks like a house really, but anyway. Now we've got to remember in the rocket we have the astronaut, and the astronaut is sitting in a chair, but that chair is oriented in that direction. Okay. It minimizes the G forces on them. So we have the pull of gravity exactly the same, Fg, going in that direction. Now here we had a tension force going up, but here there's no tension force, there's no string. So what is the force that is opposing the gravitational force going down? Well, it's the force of the chair against the body of the astronaut, and we call that the normal force. So the normal force and the gravitational force are equal and opposite, right? Because at the moment he's not sinking down into his chair and the chair is not going to the floor. That would indicate that the gravitational force is stronger. And he's not floating upwards, he's staying where he is. So the net force, just like we have over here, was 0. So if we were to do the same thing there, the net force in the y direction was the normal force plus, I hope that I haven't run out of space there, but anyway, plus the gravitational force going down. Remember I said the net force was 0 because he's not moving up or down, which we would expect that anyway, right? Which we've just said here a moment ago. So equal and opposite forces, you're not going anywhere, right? So the same sort of situation there is what we had over here is if the normal force is equal to minus mg, right, then really that's the same as the weight. So once again we've shown this here, that the apparent weight, right, the apparent weight, because this is also equal to weight, is divided by the true weight gives you 1. So at the ground level, and even just holding an object, G experienced by the person or by the scale, right, is 1.